The Grand River at Comstock Park crested at 15.7 feet yesterday. That number means almost nothing in isolation. In context, it means that river has been fighting flood stage for days, not hours. The soil around it is not absorbing anything anymore. It is full. It is done. What that cresting line represents is not a river that rose. It is a regional water table that has hit its ceiling, and the water has nowhere left to go except across the roads, through the door frames and into the ground floors of homes in Plainfield Township, where people are still waking up to this. That number, 15.7 feet, is the starting point of what I need to walk you through today. Because at the same moment that river was sitting above flood stage in Michigan, the National Weather Service was issuing a coastal flood watch covering Palm Beach, Martin, St. Lucie, and Indian River counties in South Florida. 1 to 5 inches of additional rainfall on top of already saturated coastal land, on top of a high tide cycle, 1,500 miles away, simultaneously. At the same moment, the Storm Prediction Center had critical fire weather risk, level 2 into level 3, active across parts of the southeast and central plains. Relative humidity readings below 25%, wind gusts running 15 to 25 miles per hour, red flag warnings touching millions of people. At the same moment, the Jess Fire was burning in Modoc County, California. The Sargent Fire was active in the Florida Panhandle. 42 large fires burning nationally, covering more than 113,000 acres of active ground. At the same moment, electron flux in the 2 megavolt band exceeded 1,000 particle flux units, triggering an alert from the Space Weather Prediction Center. Solar activity was low, C-class flares only, but the radiation environment around this planet was nudging into alert thresholds. At the same moment, a magnitude 3.5 earthquake registered in Texas, a 2.3 near Bonanza, Oregon, a 2.1 near Nyland, California in the Imperial Valley, sitting right on top of the San Andreas transform system. And at the same moment, scattered thunderstorm cells across the central and eastern United States were producing isolated wind gusts above 50 miles per hour. That is 10 simultaneous events across 5 distinct hazard categories in one calendar day, April 8th, 2026, yesterday. Stay with me, because what this adds up to is something they are only beginning to say out loud. If you have not subscribed to this channel, this is the moment. Hit that button. What I'm about to break down is not a collection of unrelated headlines. It is a portrait of a system under stress, and the reading I am getting off this data is one that serious analysts are watching very carefully right now. Here is what the calendar says. April 8th is spring. It is supposed to be the shoulder season, the transitional corridor between the cold, static air masses of winter and the fully loaded convective engine of May and June. The textbook spring pattern says moisture is climbing northward, the jet stream is still relatively far south, and the atmosphere is sorting itself out. Moderate instability, scattered rain events, isolated severe weather, maybe some late-season snowfall in the northern tier. Nothing synchronized, nothing stacked. That is what the climatological baseline tells you April 8th looks like. Now here is what the data actually showed yesterday. The Grand River cresting at 15.7 feet is not a surprise if you look at the antecedent precipitation in Michigan through late March and the first week of April. What is significant is the duration. Flood warnings were still active across multiple Michigan counties as of yesterday, not because a new rain event had just hit, but because the system has developed what I can only describe as a hydrological memory problem. The soil is at effective field capacity. Every additional millimetre of rain that falls is immediately surface runoff. The lag between precipitation and river response has collapsed to near zero. That is an extreme operating state. When a catchment basin hits this condition, you're no longer dealing with a flood response. You're dealing with a flood that does not end until the watershed drains. That takes time. That takes dry days. Yesterday, those dry days were not coming. Simultaneously, the South Florida Coastal Flood Watch was not being driven by the same mechanism. In South Florida, you have a completely different engine. You have subtropical moisture being dragged on shore by the pressure gradient off the Atlantic. You have high tide cycles compressing the drainage margin. And you have urban infrastructure in low-lying coastal counties, Palm Beach, Martin, St. Lucie, Indian River, that is not designed to handle the convergence of 1 to 3 inches of rainfall in 6 hours on top of a high tide event. The NWS watch covered potential localized totals of 3 to 5 inches in spots. On coastal land that is already at mean sea level in significant portions, that is not a flood watch. That is a bathtub with no drain that someone left the faucet running in. 2 completely independent hydrological emergencies, Midwest and Southeast, both active, both above threshold, same day. Then the fire signal enters the picture, and this is where the setup gets statistically unusual, in a way that I want to be precise about. Critical fire weather at level 2 to level 3, as defined by the Storm Prediction Center, requires a convergence of 3 conditions simultaneously: relative humidity below 25%, sustained winds in the 15 to 25 miles per hour range, and dry antecedent soil or fuel moisture conditions. The significance is not that any one of those conditions appeared yesterday. Each of those conditions alone is common in spring. The significance is that they converged at level 2 to 3 intensity across both the southeast plains and parts of the west at the same time that 2 separate flood systems were active in the same country. That is not the behavior of a chaotic, unorganized spring atmosphere. That is the behavior of an atmosphere with deeply contrasting moisture and dryness regimes operating simultaneously at their respective extremes. The dry air is extremely dry. The wet regions are extremely wet. The gradient between them is sharp. That sharp gradient is the engine. Stay with me. In meteorological terms, what creates a steep moisture and temperature gradient across a continental landmass in spring is an active and amplified upper-level pattern. The jet stream is not running in a gentle, nearly zonal flow across the country. It is looping. It is dipping deep into the southern tier in some locations and riding anomalously high in others. Where it dips, it wraps cold dry air southward and westward into regions that are currently experiencing fuel conditions primed for rapid fire spread. Where it rides high, it acts as a conveyor belt for Gulf moisture being pumped northward into the mid-continent, loading the lower atmosphere with the kind of precipitable water content that collapses the soil saturation curve in river systems like the Grand River Basin. Isolated severe thunderstorm cells with gusts above 50 miles per hour in the central and eastern United States yesterday were the visible surface expression of that gradient. That is the atmosphere expressing its instability. Those gusts above 50 miles per hour in convective cells are not random. They are the pressure release valve on a system that is trying to equalize 2 very different air masses that are currently sitting next to each other in a configuration that does not naturally want to be stable. This is the loaded gun structure. When a jet stream pattern amplifies like this in spring, it creates what forecasters call a split flow regime. One branch of the jet carries energy across the northern tier. The other branch dips through the south. Between those 2 branches, the atmosphere is caught in a reinforcing loop. The southern branch keeps pulling moisture from the Gulf northward, which feeds the flood events. The northern branch keeps suppressing that moisture from exiting, which means it stalls and dumps. Meanwhile, on the western side of the trough, the dry continental air is being dragged southward and eastward by the same large-scale circulation, directly into regions like the Florida Panhandle and the Southeast Plains where the Sergeant Fire and the critical fire weather setup were active yesterday. You're not looking at isolated events that happen to share a date. You're looking at one large-scale atmospheric machine expressing itself in multiple extreme modes simultaneously. The floods and the fires are not contradictions. They are the same pattern wearing different faces. The Jess Fire in Modoc County, California represents a separate but related signal. Modoc County sits in the northeastern corner of California, a high desert terrain that receives limited Pacific moisture. When that region lights in the early April, it reflects a drought stress in fuel moisture that is weeks or months in the making, not just yesterday's wind event. The fact that 42 large fires were nationally active as of April 8th, burning across more than 113,310 total acres, tells you that the Jess Fire is not an isolated ignition. It is part of a mosaic of fire activity that has been building across the western fire season envelope, and that envelope is opening earlier than climatological norms would suggest for the second week of April. Now I want to stay on Florida for a moment, because Florida is showing the system something unusual, and it deserves focused attention. In the Florida Panhandle yesterday, the Sergeant Fire was burning. Active fire behavior, structures threatened, part of a regional southern area fire complex exceeding 24,000 acres. At the exact same time, the southern peninsula of Florida, less than 400 miles away, was under a coastal flood watch with potential rainfall of up to 5 inches. One state. Fire in the north, flood in the south, yesterday. That is not a geographic quirk. That is the spatial expression of that sharp atmospheric gradient I described. The jet stream's influence and the moisture boundary were running directly through the state. That kind of in-state fire-flood simultaneity creates an emergency management challenge that is almost impossible to model in advance. Resource allocation systems in Florida were being asked to simultaneously support flood response on the peninsula and fire suppression in the Panhandle. The operational bandwidth required for that is significant, and when those two demands exist in the same 24-hour window, the blind spot risk escalates. The blind spot is the night window, and it is the most underappreciated hazard amplifier in these stacked multi-hazard scenarios. Here is why. River flooding at stages like 15.7 feet on the Grand River does its most severe work after sunset. Not because the physics change, but because the human awareness does. A road that was passable at 4 p.m. can be underwater by 11 p.m. as the crest slowly propagates downstream through the system. Hydrological lag in saturated catchments means the peak flood expression at individual points along the river can occur hours after the rain that caused it. The NWS can issue a warning, and it is technically accurate, but the geography of the flooding shifts continuously as the water moves. At night, with reduced visibility and reduced emergency response staffing, a motorist encountering a flooded road at speed has a dramatically reduced margin. Turn around, don't drown is the phrase, but the phrase assumes the driver has daylight to read the water's depth. It assumes the warning reached them. It assumes they have a route alternative. In the hours between midnight and dawn in a saturated river basin, none of those assumptions are reliable. The fire side of the blind spot operates differently but is equally severe. Fires in the Sargent complex and across the Plains fire weather zone that are making active runs during the afternoon wind event, which is the highest intensity period for fire weather, can lay down deep heat in the soil and in the fuel bed. After dark, wind speeds typically decrease, and fire managers often assume the fire is moderating. But in conditions with residual heat deep in the fuel bed and terrain that can channel drainage winds in unexpected directions in the early morning hours before sunrise, reactivations can occur faster than detection systems can track. If a fire makes a run at 3 a.m. in a terrain that produces its own local wind patterns, the detection to response timeline stretches to a critical degree. The electron flux alert from the Space Weather Prediction Center, with 2 megavolt flux exceeding 1,000 particle flux units, adds one more layer that I want to be careful about characterizing accurately. The KP index was running 1 to 3, which is quiet. No major coronal mass ejection event was in progress. This is not a geomagnetic storm. What it is an indication that the radiation belt environment around Earth was showing elevated particle energetics consistent with a solar cycle that is transitioning upward from minimum. The operational significance in a multi-hazard environment like yesterday's is not extreme, but it is a background stressor on the technological infrastructure that supports the response to every other event on this list. Satellite-based GPS accuracy can degrade under elevated electron flux. NOAA weather satellites, fire detection platforms, and the emergency communication systems that tie flood warning networks together all operate in that same electron flux environment. When that environment is elevated, even at alert threshold rather than storm threshold, you are introducing marginal additional uncertainty into systems that are already being asked to perform at high capacity. Think of it as a slight reduction in the signal clarity of the very instruments you are relying on to see the full picture of what is happening across these 10 simultaneous events. Now, the seismic data. I want to be direct about what it means and what it does not mean. A magnitude 2.3 near Bonanza, Oregon, and a magnitude 2.1 near Nyland, California, do not represent imminent major earthquake threat. They do not signify unusual strain release events in isolation, but they are data points in a monitoring environment. The Imperial Valley near Nyland sits at a junction of the San Andreas Fault System's transform boundary, one of the most carefully watched sections of the entire Cascadia and California fault network. A 2.1 at 9 to 10 kilometers depth in that region is a routine microseismic event. What makes it worth noting in this context is not the magnitude, it is the clustering. Bonanza, Oregon, monitoring seismicity in the Cascade subduction zone environment. Nyland, California, on the southern San Andreas system. A 3.5 in Texas, reflecting intraplate stress in the central United States. A region where induced seismicity and natural fault stress interact in ways that are still being characterized. 3 separate seismic regions showing activity on the same day. Again, routine individually. The question the data is asking you to hold is why you are noting them at all, and the answer is that in a multi-hazard monitoring environment, seismic background noise is part of the total system state. These are not alarms, they are readings, and the readings are in. The thunderstorm signal across the central and eastern United States yesterday, producing isolated cells with gusts above 50 miles per hour, is the system introducing itself. That phrase matters. What you saw in those convective cells yesterday was not the headline event. It was not a historic outbreak. The SPC did not issue high-end severe weather risk days. But what those cells were doing was something more significant than their individual severity ratings suggest. They were the first kinetic expression of an atmosphere that has loaded enough instability into the lower and mid-levels to produce sustained organised convection. 50+ miles per hour wind gusts from a cell that does not even reach significant severe status tells you about the thermodynamic depth of the environment that cell is embedded in. When a cell can produce damaging winds without being particularly organised, the atmosphere around it has done most of the work for it. That is a background kinetic energy signature. It is the system showing you what it has available to spend, and it spent only a small fraction of it yesterday. The temperatures running above normal across the central and eastern United States yesterday added the final component. Warmer than normal surface temperatures in April accelerate the boundary layer mixing that supports convection. They also accelerate soil moisture evaporation in the regions that are not under precipitation, which means the fire weather zones dry faster between rain events. Above normal warmth in a system that is already showing split flow jet stream dynamics, simultaneous flood and fire activity, and background radiation belt stress is not an additive hazard. It is a multiplicative one. Warmth makes the wet regions wetter through increased Gulf moisture transport. Warmth makes the dry regions drier through increased evaporative demand. Warmth deepens the atmospheric instability that produces the convective cells that deliver 50+ miles per hour gusts. The temperature signal is not its own hazard category yesterday. It is the fuel that all the other hazards are burning. The models are talking to each other. What I mean by that is that the pattern type generating these simultaneous signals, the amplified split flow, the sharp moisture gradient, the soil saturation in the north, the drought stress in the south and west, the elevated radiation environment, the seismic background noise, all of these are not being generated by different unrelated causes. They are being generated by a season that is running fast and a large-scale atmospheric state that is expressing deep contrasts simultaneously. The models that track these patterns have been converging on a spring season that is operating at the extreme margins of its normal envelope. Yesterday was not a theoretical convergence. It was a measured, documented one-day expression of that convergence, with 10 simultaneous verifiable events across 5 hazard categories. This is the part they are reluctant to say out loud. The operational challenge of a multi-hazard day like April 8, 2026 is not any single event. It is the bandwidth drain. Emergency management resources, forecasting attention, media coverage, public awareness, sensor network capacity, they all have limits. When 10 events compete for those limits simultaneously, the events that fall below the threshold for headline coverage do not disappear. They continue. The Grand River does not wait for the news cycle to have space for it. The Jess fire does not pause while the Sargent fire gets attention. The electron flux environment does not recalibrate because the GPS system servicing a fire crew needs better signal. The compounding is not atmospheric, it is operational, and that operational compounding is invisible in the data because it lives between the data points, in the response lag, in the stretched resource, in the warning that reached 90% of the affected population and not the other 10. What April 8th showed is a system in a configuration that the climatological baseline for early April does not predict should exist at this intensity, this broadly distributed, and this simultaneously. The Grand River did not crest at 15.7 feet because April is a wet month. It crested there because weeks of accumulated precipitation met a saturated soil column in a watershed that has no remaining absorption capacity. That is a chronic signal expressing itself acutely. The fire weather did not reach level 2 to level 3 in the southeastern plains because April is a dry month. It reached that level because a moisture gradient created by the same large-scale pattern that caused the flood's concentrated dryness in adjacent regions with precision. The fires are not happening in spite of the floods. They are happening because of the same atmospheric engine. The system is not broken. It is working exactly as the physics say it should, given the inputs it has received over weeks and months. The inputs are the anomaly. The outputs, 10 simultaneous hazard events on April 8, 2026, are simply what those inputs produce. What happens when the operational infrastructure of a country is asked to manage a spring season that is running multiple simultaneous extreme modes at once, not for one day, but as a sustained pattern across weeks? The system is still loading.